session talk by Gianpaolo Piscitelli. We'll talk about the first Robin Neumann eigenvalue as a parametric quantitative.
Okay, thank you. Thank you all to the organizers for giving me the possibility to have this talk. Okay, in this talk I will speak about a particular eigenvalue problem with different boundary conditions. In this case, Robin and Neumann boundary condition, and in particular I will describe a result on an isoperimetric inequality and the related stability result. Okay, first of all, in this slide I want to fix the notations. I will call omega 0 and theta two bounded domain such that omega is well contained in omega 0. In the following, I will call the boundary of omega 0 the outer boundary and the boundary of theta the inner boundary. On the outer boundary and on the inner boundary, we will consider different boundary conditions. The problem that I am going to treat is the following. In a variational form can be represented by the classical Rayleigh quotient between the square of the magnitude of the gradient of the unknown function and the square of the function, plus a boundary term depending only by the outer boundary. This problem can be also written as the classical Laplacian eigenvalue problem with the Robin boundary condition on the outer boundary and the Neumann condition on the inner boundary. In this case, beta is a real parameter. Okay, this is the problem that I want to study, and these are the motivations. We have decided to start studying these problems, this kind of problem, by the following motivation. The first of all is the generalization of the classical the classical Faber-Cran inequalities. In the more simple case, the Laplacian eigenvalue for the Dirichlet on the full domain, also that is on a classical domain, when the condition u equal to 0 on the outer boundary, the classical Faber-Cran inequality says that the ball is a minimizer for in the class of the domain when we fix the measure. This result has been proved by Faber and Cran, and then by Bossel and Danners when we replace the Dirichlet condition with the Robin Dirichlet condition for positive value of domain. And then this result has been developed also in many other directions. So the following question is what happens when beta is negative? When beta is negative, in this framework now, in these slides, these first slides, we are talking only on full domain without any holes. When beta is negative, Barrequet in 1977 conjectured that the ball now is a maximizer among domain with fixed measure. So for beta positive, the ball is a minimizer. For beta negative, the ball is a maximizer. Then Ferone, Nietzsche, and Trombetti in 1915 has shown that when the ball is in some sense when the domain is in some sense close to the ball, then the ball is a maximizer. Again, and then furthermore, Freitas and Krejcik showed that when beta is negative but small, then again the ball is a maximizer. But they were also able to prove that if beta, the magnitude of beta is great enough, then the eigenvalue reached by the spherical shell is greater than the eigenvalue on the ball with the same measure. And so this is the starting point of our research, in the sense that since the spherical shell is greater than or realizes an eigenvalue greater than the ball, so we are starting to think to the holed domain, to the domain with holes. And so in the class of the domain with holes, the optimal shape candidate is the spherical shell. So starting from these motivations, we have found in literature an old work by Payne and Weinberger. In this work, Payne and Weinberger proved that only in the plane and only for the Robin case when we fix the measure and the outer perimeter, the annulus is a maximizer. So our idea was to generalize this result to any dimensions. This result is mainly based on two key concepts. The first concept is the definition of the set. So in this in the proof of this result, it's important to define the inner parallel set, that are the sets with the same shape, but inside with the same shape of omega. So the sets with the distance from the outer boundary lower than a fixed parameter delta. So this is for the sets. Regarding the functions, we have to use some particular test functions depending only by the outer distance. And the idea is that this test function can map the point with fixed distance from the outer boundary of omega to the point with the same radius, because we are thinking to move from omega to the annulus. So this is a picture of the eigenfunction on the annulus, and it's realized with the use of a free ferm. Okay, so in collaboration with Gloria Paoli and Leonardo Trani from University of Naples, we were able to prove this isoperimetric inequality. For that, the spherical shell is a maximizer when we fix the measure and the outer perimeter. And the outer perimeter.
So what's the difference between this and the previous one?
This is in higher dimensions.
Higher dimensions.
Yeah, for n greater than 3. The work of Payne and Weinberger was also for the bidimensional case, also all in the plane.
But you didn't have beta less than 0 in the previous one, or you did?
No. Okay, this in this paper you will find the result for beta greater than 0 and for beta lower than 0. But from now on, I want to focus only on the negative value of the parameter. Why? Because for the negative value of parameter, we are also able to prove the stability result. Okay. Let's focus on this. Okay. The idea, the main tools for the proof are again the same. We have to find a suitable class of domains and a suitable test functions. Particularly, the test function that we have used falls in the class of the so-called web functions, that are functions only depending by the distance from the outer boundary. The name web function first appeared in a paper of Gazzola in 1999. This function is constructed in this way. This function capital G is very particular, but it's important to say that it's an increasing function. It's an increasing function depending by the distance, and this function preserves the magnitude of the gradient of the unknown function on the level sets of the eigenfunction of the annulus. The maximum of this function w is equal to the maximum of the function zeta. Zeta is the eigenfunction on the annulus. And okay, with this picture probably is better to explain what I am doing. So I have this test function w, that is an increasing function, is decreasing with respect to the outer from the distance to the outer boundary, and I am considering the sub-level set the sub-level set of this function w. This is the main idea. Okay. Regarding the function. Regarding the sets, the class of admissible sets now is easily seen that is the class of the domain omega, such that omega is omega 0 minus theta, where theta is inside omega 0, with the constraint on the measure and on the outer perimeter. But to prove the stability results, we also need to add two conditions. The first one means that the two boundary has not to touch each other, and the second one means that is a non-degeneration condition, in sense that the inner set theta cannot be a point or a line. Okay, and thanks to the isoperimetric result, in this class of domain, the spherical shell is the maximizer. Okay, so after the definition of the test function, a very particular test function, and after the definition of the sets, we need, as a last tool, to define the nearly annular set, in the sense that we need to define some sets that are in some sense near to the spherical shell. In literature is known the definition of nearly spherical sets, that are sets near close to a sphere. The nearly spherical sets are sets that are parameterized by this function u, that in some sense is the measure of the distance of the boundary from a fixed radius, in this case r. Indeed, if u is equal to 0, this is the parameterization of a ball, of the boundary of the ball. This kind of parameterization is very useful because we have an explicit expression of the measure and of the perimeter. So, if we have this definition in mind, with the same spirit, we can define the nearly annular sets. The nearly annular sets are wholed sets, such that the outer boundary is parameterized by a function u, and the inner boundary is parameterized by a function v. The first one measured the oscillation from the ball with the radius r2. The second one, in some sense, measured the oscillation from the ball r1. So with this double parameterization, we define the nearly annular sets. So with this picture, I will better explain. So we have to measure, in some sense, the distance between these two and the distance between these two. So before speaking on a stability result, we have to define an asymmetry. What kind of asymmetry is suitable in this framework? So we have find this kind of asymmetry. Regarding the outer box, we use the classical Hausdorff asymmetry that measure the Hausdorff distance from the two boundaries. The boundary of the ball BR2, bigger ball, and the boundary of omega 0. And it's almost classical, this Hausdorff asymmetry. Regarding the inner asymmetry, regarding the inner box, we have to introduce, so starting from zeta is the eigenfunction on the annulus, on the spherical shell. W is the wave function that I defined before, and I need to introduce the inner parallel sets. Inner parallel set of omega 0. That is a set with the same shape of omega 0, but inside, with the fixed, where the distance is greater than a fixed value. The choice of this fixed value is such that the measure of this inner parallel set is the same of theta. Now with the picture probably is better. So regarding the outer box, we compare omega 0 with BR2. Regarding the inner box, we compare theta not with BR1, the inner ball, but with the inner parallel K. So we have to find an estimate of the asymmetry using theta and K. In particular, we will use this green region, that is the set theta minus K, the set theta minus K, and we define a Frankel asymmetry, a Frankel type asymmetry, with the weight, where the weight is the difference between the test function W and the eigenfunction on the annulus. So summing up, for the outer boundary there is a classical Hausdorff asymmetry. For the inner boundary we have this Frankel type asymmetry. Okay, so the hybrid asymmetry that we are introducing is simply the maximum between these two asymmetry, the inner and the outer asymmetry, the Hausdorff and the Frankel asymmetry. Okay, the first one is not exactly the Hausdorff asymmetry, but is G of the Hausdorff asymmetry, but G is very useful, very common in this context. Okay, so let's focus on this. Let's focus on this definition of symmetry. So the first question is if it is a good asymmetry. Okay, the question is that the point is that, and why we have called this a weak asymmetry, and if it is an asymmetry, why we have called this a weak asymmetry? Because in any case, the Frankel type asymmetry is in any case greater than 0, and this is good. But it could be 0 also if omega is not the greater ball and theta is not the inner parallel. In this case, if the Frankel asymmetry is 0, then this means that omega 0 is not the ball, and this means that the Hausdorff asymmetry is greater than 0. So this on one end. On the other end, if the Hausdorff asymmetry is 0, this means that the inner parallel set is the ball, and in this case is different from theta, and so the Frankel asymmetry is greater than 0. So summing up, what I want to say is that if the Frankel asymmetry is 0, then the Hausdorff asymmetry is greater than 0. If the Hausdorff asymmetry is 0, then the Frankel asymmetry is 0. So actually, the hybrid asymmetry is 0 if and only if omega is the spherical shell. So yes, it is properly an asymmetry. Furthermore, we are also able to prove that if we have some set that approaches, if a sequence of sets approaches the spherical shell, then with the Hausdorff instance, then the asymmetry tends to 0. And if the asymmetry tends to 0, means that the sets approach to spherical shell. So yes, it is a good asymmetry, so we can use this asymmetry to give our stability result. Okay, and then in collaboration with Simone Cito and Gloria Paoli, we were able to prove that really we were able to prove these stability results, and pay attention that this constant depend on the geometry of the set omega and also by a constant beta. So next step for this to improve this result could be to remove the dependence by beta. Okay, the strategy of the proof is the following. We first estimate the outer asymmetry, then estimate the inner asymmetry, and then take the maximum. Okay, the two proofs are separated and the two strategies are different. Okay, regarding the first step, regarding the outer asymmetry, we will use an auxiliary problem treated, for example, by Badol and Wagner, Feronic and Trombetti, and Cito Lamanna, where we use to compare our eigenvalue problem lambda with this Steklov type eigenvalue problem sigma. This is a Steklov problem on the outer boundary and Neumann on the inner boundary. Is almost a Steklov problem because also we have to add the unknown function in the equation in omega. This problem is related to this problem sigma is related to our starting problem lambda, because if we consider the solution, the radial solution, and we test the radial solution on the set on the eigenvalue sigma, we are able to prove that we have this stability result. It's a computation, it's a very hard computation, but in the end we were able to prove that we have this stability result for sigma. So to obtain the stability result for lambda, we know that there is a relation between lambda and sigma that is based on some scaling properties. So from the results of the stability on sigma, we obtain the stability result on lambda. Okay, I want to skip this. Okay, this is regarding, so the idea on the first step is to move to this auxiliary problem. Regarding the first step, the second step is more simple because we divide the set omega 0 into three regions: omega 0 minus theta, theta minus k, and the intersection of theta and k. So these three regions are then represented by the green and the blue color. This term by the these three terms, the first term is represented in red and the second term in blue, and we have this inequality. The first inequality comes from the isoperimetric inequality proof. This inequality comes from the fact that on k minus theta, w is constant and is constant to the is constant and is equal to the minimum of the eigenfunction zeta. And so and we have also we are using also a measure constraint. So by comparing these with these two last terms goes away, and by passing this term to the right hand side term, we have the following. We have the following estimate on the integral of omega squared. This is important because we can use it in the estimate of the Rayleigh quotient to obtain the result. The Rayleigh quotient is composed by these three terms. The term that I have showed 1 second ago is the denominator term. By using the previous inequality in the denominator term, remember that this is negative, and also all this eigenvalue is negative. If beta is negative, lambda is negative. So we have the reversed inequalities. We obtain by algebraic computation the final result. Okay, and by joining no, sorry. Okay, by using only the first and the last term of this chain of inequality, and by algebraic computation, we obtain the stability result also for the inner box. So by joining the inner and the outer, we obtain the result. Okay, if I have just 1 minute, some open problems. Okay. First of all, the first open problems, the first perspective was in improvement of the asymmetry. We have found this kind of asymmetry, but as I have showed some minutes ago, this asymmetry can be improved. Okay, another point could be, another open problem could be to enlarge the class of the miscible sets, for example, by considering only one constraint, the measure or the perimeter, and not both of the constraint. Third open problem is a generalization to nonlinear case. Regarding the inner asymmetry, it is done and is also shown in our first paper. But regarding the outer asymmetry, no, because the Hausdorff asymmetry is highly related to the linear case, so we have no idea at the moment on how to prove it. And another improvement could be the improvement for the case of positive beta. Our method works only for beta negative because it's related to the auxiliary problem, the auxiliary stack of problem, and this method cannot be used in this case. Okay, if I have just 1 second, I want to invite you next week in Naples. I'm organizing this this conference on elliptic and parabolic problems, analytic and geometric methods, in collaboration with Professors Filomena Feo and Ida De Bonis from University of Rome. Thank you for the attention.
First, let's ask some questions before you start booking the tickets to Naples. An hour later, we have a reception. You can do it there. All right. Any